Okay, so now we're going to continue with our second bit of our graph theory lecture for today. I'm going to give you the motivating example for the really how this whole theory was founded, which, funny enough, is what all of chapter 5 in the textbook is about. So, chapter 5 discusses what we call Euler circuits and paths. This is actually pretty good because Euler was a mathematician, the mathematician who is credited with founding graph theory in the 1700s. And so we're going to talk about the original example. So the motivating example, this is a problem called here, I'll erase that underline. The bridges of Königsberg. So Königsberg was a city in Prussia. It's now a city in Russia. And back in the day, in the 1700s, the city looked like this. So Königsberg, Prussia, 1700s, had 18th century. Was a city with a river running through it. In the river were 2 islands and 7 bridges connected the land masses as shown below. So I'll make a little picture. So my picture will be, so here's our river. Here we have Königsberg. So there's our river, and in the river we're going to have 2 land masses. So why don't I call it here. I'm going to actually use black, and then I'll do blue for the... So there's our river. Here are 2 land masses in the river. Islands. And the bridges were like this, so we'll say this is water. Okay. And the bridges looked like this. There was one bridge going from the big island, from the west side of the big island to the north shore, another bridge from the east side of the big island to the north shore, and another bridge on either side of that one, like that. Bridge like that. One like this from that bit, and one like this. Okay? And so here, say we have the downtown up here, and alright, good. And so the idea is that these 7 bridges So we're famous. We're built by a famous architect. I don't know, designed by a famous architect. And the city wanted to have a tour of all 7 bridges crossing each bridge exactly 1 time. And end back at the starting point, like most tours, right? If you start the tour at one place, you expect to end the tour at that same place. And this actually really stumped people. They kept on trying to figure out how to do it, and it just didn't quite seem doable. So let's see, why not? Well, say that we put our starting point up here, right? So let's say that this is our starting point. And then from there, so from our starting point, we have to say we'll take this bridge first. Okay, so we come down there, and now we're on this island. And then what do we want to do? Maybe we take this bridge next, and we go down to this. And then we come back along, and we'll go up maybe this bridge back onto this island. Now we have to choose. Maybe we'll take the bridge that connects us to the other island now. And then we can take this bridge maybe. Oh, but now we're stuck. Now we're stuck down here. So maybe that's not a good one. Okay, so instead, let's do the same thing where we came down there and up there. Maybe now instead we could take this bridge up here, and then take this one, and then, if we take this one, now we're stuck, and if we take this one, now we're stuck. So this was really frustrating people, and people were pretty confident that it just wasn't possible. They just couldn't find a mathematical way of expressing that. So people were quite sure it was impossible. But nobody had a mathematical way to prove this. Until Euler. Okay, so Euler proposed that we turn our map into a graph. And our graph is going to have the vertex set V is going to be the set. Remember, this is our vertex set. V is going to be our set of land masses. And our edge set, E, is going to be pairs of land masses which are connected by a bridge. And so look, again, we can simplify a problem into just a set and pairs of elements from that set. That's really what this comes down to over and over again. Again, just a set and pairs of elements from the set. And we remember that there's n times n minus 1 over 2 pairs that we can possibly make. Good. Okay, and so what does this look like then when we turn this? So now our graph, which was this up here, why don't I copy this picture? is going to turn into a different kind of graph. So now why don't I paste it, I don't know, paste it there. I'll shrink it down. And what I'm going to do is I'm going to make out each landmass into a thing. So, oops. Why don't I label the landmasses in red? A, B, C, and D. Nah, I'll do it more like a clock. A, B, C, and D. And now, so I'll draw those as just A, B, C, and D. So now they're just what we call nodes, or vertices. Okay? And now bridges are going to be edges, right? So now our bridges are going to be A and D are connected by 2 bridges. D and C are also connected by 2 bridges. A and B are connected by a single bridge. B and C are connected by a single bridge. And D and B are connected by a single bridge. So this picture actually turns into this one. And if we want to simplify it even further, we can just not even label our land masses and just have the pretty picture that looks like this. Okay. Notice that we can also rearrange this any way we want. So to put it flip it over, rotate it, all is good. Now we have a graph. Sorry about that, edge is not pretty. To represent our problem. Now Euler's solution was still pretty tricky. I mean, it's still a pretty cool solution. So I wonder if you can see what the problem is with this. So if we start at A, and we have to go there, take a bridge, then we go back on this one, and then we leave A on a third bridge, and now we don't have another bridge to come back to our starting point on. And so that's exactly the heart of the problem, is that actually we can only do this if we have an even number of bridges going out to A, because every time we leave, we need to come back. And that makes 2 bridges, so it means it needs to be even. So Euler's circuit theorem this is possible. So actually I'll just say Euler's solution, and then I'll write down the theorem in a bit. Euler's solution says that this is impossible. Why is it impossible? Well, it's impossible because some land masses, vertices, have an odd number of bridges, edges. Okay, and why is that a problem? Well, so the problem with an odd number is that whenever you have so let's look at this graph up here. Say we pick a vertex with an odd number, right? So you have to leave that vertex along one bridge, and then you do whatever you want over here, and then you still have to come back to that vertex at one point, and then you have to take the third edge away, and now you can't get back again. Okay? So that's the idea. This is impossible under conditions one, every edge must be, or every bridge must be walked. Once. And 2, we end and start at the same point. Okay. So this is really quite a cool solution. He said that not only is it, I mean, that one's kind of obvious. So, under the conditions, 1, every bridge must be walked once. 2, we end and start at the same point. We must have every vertex with even degree. This is a quick definition here. The degree of a vertex is the number of edges which are attached. As we say, incident is what we say in graph theory terms to that vertex. Okay? So the degree of a vertex is the number of edges which are attached to it. So in that sense, the degree here is the number of bridges coming out of a landmass. And so Euler's theorem, Euler's circuit theorem, says something stronger. Namely, that a tour, as previously described, and actually, I'll say, I'm going to call it what we call it because we've named these tours a specific name. We call them Euler tours. So an Euler tour or circuit, as previously described, is possible if and only if every vertex has even degree. So this is really big. So not only is it not possible to do an Euler circuit if some vertex has odd degree, but it's always possible to do an Euler circuit if every vertex has even degree. So not only is it impossible when some vertex has odd degree, but it is possible whenever every vertex has even degree. So this is quite, this is really something. So it's possible whenever every vertex has even degree. This means I could draw any kind of city with a river running through it, multiple rivers running through it. Why don't I say, like, I could even make a more interesting one. Maybe this city has like a little, you know, so a little river that meets up with the big river, and then like 1, 2, and 3 islands in the middle there. I'll draw them better. And maybe now we have, and remember, so this will all be water. And maybe now we have a bridge crossing there. Oops, I forgot to do. And now maybe we have a bridge crossing there and there. And say we want to connect this island to the middle island to that bottom one, and we want to connect it to the top left and the top right bit. Well, now this island, this middle island, has degree 3, but maybe we want to connect it to the right-hand island, and maybe now we want to connect this right-hand island up to the top. Although now the top left and the top right have degree 3, so why don't we do another one? Let's say that we have actually 2 bridges coming out of this one. Or even better, why don't we do another bridge joining the 2 of them up there? And then we can have, so we kind of want to connect the right one to the bottom, right? But now it's got degree 3, but so does the bottom, so we could do another bridge like that. Now they've all got even. Good. So now everything's even. Can't get from the left island to the middle island without hopping over, but that's fine. Okay. So I claim, or rather, Euler's circuit theorem tells us that we can find an acceptable tour. Now we can actually use an algorithm to you do this. We can actually use an algorithm to find a route. And this algorithm is going to be called Fleury's. It's named after a mathematician, so this is Fleury's algorithm. And it basically says this. First step, check that every vertex has even degree. And second step is going to be to pick a vertex, V, and walk along any edge from V. Okay? And the idea is that in the middle, so you choose the starting vertex, and you walk along any edge. And the only trick to the algorithm is that you always want to stay as close to V as possible. So, walk along any edge from V. At every step, remain as close to V as possible. i.e., if you have the choice, always return to a previous vertex before exploring a new one. Before walking to a new one. We actually do talk about walks in graph theory. So lots of these things have lots of graph theoretical subjects have very intuitive names, which is cool. Okay, always return to a previous vertex before walking to a new one. Okay, and then finally, you just keep on doing this. Repeat this process until you end up back at the start. Okay? So let's give this a go. Let's see how it works. So I'm going to take my graph here, my random graph that I just drew. I'm going to copy it. I'm going to come down here. I'm going to paste it. Example. Okay. And I'm going to turn it into a graph. Okay. So this is going to turn into the graph, which has so we have one landmass in the top left, one landmass in the top right, 3 landmasses in the middle, and 1 at the bottom. Okay. And how am I going to draw this? Well, this one at the bottom is connected to all 3 ones above it, and the one on the right has 2 bridges. Now these middle ones are connected by an edge like that, but these ones aren't connected. This one goes up to here. This middle vertex is connected to that landmass, which is precisely this edge right here. These top 2 landmasses are connected by 2 bridges. So we'll draw those as edges like this. The top left landmass is connected now to the middle one and the left-hand island. So we'll draw those connections. Middle island, left-hand island, and I think that should be it. Yep. So this is all of the connections that we have. So let's use Fleury's algorithm. So we're going to pick. So Fleury says pick, I'm going to put V in red. So why don't it just says we can pick any one, because the first step is to check that we have all even degrees, but that's how I built the graph to begin with. So I'm just going to say pick V. That's going to be our vertex. Okay? And now all we're going to do is we're going to pick, so the first bit of the algorithm said walk along any edge from V. Okay? So I'm going to walk along, I'm going to use the highlighter. I'll walk along this edge from V here. Okay, so now that I've gotten here, what can I do? I can Well, Fleury says, if I have the chance to go back to a vertex I've already seen, if you have the choice, return to a previous vertex. Otherwise, walk to a new one. Okay, so do I have the choice of walking back to V? No, because I've already taken this edge. So I've already taken this edge. Must go somewhere new. Okay. So now I'm going to take a new edge. Why don't I go over to here? Okay. So now I'm back here. And now I think, okay, so next time I can can I get back to any of the vertices I've already seen? Yes, I can get back to this one. That was step 2. So I'll go back to that one. Okay. Still haven't crossed any bridge twice. Now from here, I'm going to go... actually, maybe I should draw these as little arrows. That would be good. Yes. Okay, so instead of highlighter marks, I'm going to draw these as little arrows. Little green arrows. Okay, so from V, I'm going to take this edge to this vertex and color it green. Then I took this edge to this vertex and I'll color it green. And now I can take this edge and go back to a vertex I've already seen. And good. Now I haven't done anything new. Now I'm back at this vertex. So I only have one more edge that's unused, and that's this one, because I've already used this one, and this one, so I left it. And now look, this vertex is like kind of done. We can forget about it. And, moreover, we're left with a graph. If we forget about this vertex and delete it and all of its edges, we're left with a graph that still has even degree everywhere, except for at V. But notice that V is going to have odd degree until the very end when we come back to it. Okay, so now we've gone out to here, and now we've seen this vertex too. We've seen a new vertex. Now, if I have the choice, I should go back to a previous vertex. So that means I could either take this edge or this edge. Doesn't matter which one I pick, because Fleury isn't specific. He just says take any one. So why don't I go back to V? Okay, so now I'm back at V, and I can't go to any new one. I can't go back to any old vertices, so I'll go over here. Okay, now I'm here. All right, I can go back to this vertex, right? So Fleury tells me to do that. Then from this vertex, I can go to here. So Fleury tells me to go here. Now from this vertex, I have no real options except for this one. Get here. Only one option from there, which is to go back to this one right there. And finally, we go back to V, we take this edge back along, and we end up back at the starting point. Good. So that's really the whole thing. And this always works, which is quite cool. Good. And follow the algorithm. Okay. And so this always works. Now one thing that might pop into your head, so this popped into my head. So what if we had like this, but we always wanted to go back to the starting point. But then maybe this one goes out here and does a thing like that, right? So this is a little worrisome for me now, because Fleury says to pick our vertex V over here, and we take this edge over to here. And now, if Fleury wants us to always go back to a vertex we've already seen, it should take us back to V, but now we'll be stuck. So this is kind of interesting. I think your textbook has made a mistake. So in fact, you don't want to return to V. Actually, watch out. Following flurry here will give you a problem. Of course, we know by Euler that this is there's still a solution, and that solution is precisely this, right? You go shoop, 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 shoot, and you get back to where you started. But that's not what the algorithm told us to do. So actually, we update the algorithm given by your book on page 153 to include one more condition, one that I just came up with on the top of my head. Okay. I'll write it again. Our updated flurry alg goes like this. I'm going to cut this actually and paste it over here. Okay. So step 1, pick any vertex. 2, walk along edges to vertices to start. Already seen, and this is the important part, walk along edges to vertices which you've already seen whenever possible. Unless this means using every edge connected to V starting vertex, unless this means using every edge connected to the starting vertex. Every other, before crossing every other edge. Every. Okay, so this is definitely an important thing to update. Yeah. Unless this means using every edge connected to the starting vertex before using every other edge. So this was like our case here. We used every edge connected to the starting vertex by following the algorithm before we'd used these ones over here. Okay, and then the rest of it will be the same. So repeat until arriving back at the start once all other edges have been used. Okay, So there's our updated algorithm. So I took a lot longer talking about this problem than I thought I would. I guess that's all right. I guess next time I'll do a slightly different subject, but more graph theory. I'll probably finish the notes I had here next time and do some more real life examples. So why don't I just say that? Next time, Euler paths and some more real life applications. Okay. Good. Well, talk to you next time.